LDA, also known as linear discriminant analysis, is a type of linear combination, a mathematical process using various data items and applying functions to that set to separately analyze multiple classes of objects or items. In this video, you will see how LDA is applied in entertainment industry. So sit tight and solve a case study that involves finding information on the type of Pokemons based on its stat. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
The topic for the day being as LDA, linear discriminant analysis. But a large part of the conversation would actually go towards the application of it to a very specific case that I picked up to talk about explaining LDA from an entertainment perspective, although it has application in any field that you pick up. More importantly, whenever we are looking at higher feature engineerings, we have multiple features to play with. It kind of sets aside in parallel to yet another approach, which is called PCA. It's yet another technique to actually achieve a similar kind of an output of dimensionality reduction. So we're going to talk a little bit about that. As an agenda for the day, that's very simple. I always try to keep the agenda to the point. And the next 1 hour ride with you guys would certainly be more about what exactly is this case, what is the problem statement, and what is the context that we are discussing this in. What couple of slides to talk about LDA in general as a feature selection approach, which is more related with the dimensionality reduction, as I mentioned. What data analysis we kind of presented and what was the outcome that came out. What I'm going to do post the agenda number 4 is take you dive completely into the Jupyter Notebook to run through the code, talk more in detail about what happens as we run through the data that we were dealing with in the data for the context, how we divided to play around with the most critical variables, how the problem led us to look at certain new variables to be defined, and how primarily LDA kept its role so that we can talk a little bit about what is the importance of LDA, how do we conclude what to do when we are dealing with large number of variables. So that's the broader context for the day. So what is this case all about that we are discussing today? So this case is primarily about the information on Pokemon and the 7 generations of Pokemon. We picked up this problem to look at it from a perspective that can we predict the type of successful Pokemon character, which was the initial problem. And in the process, we also had to do something called as feature selection, feature engineering, wherein the goal was to see how we can select the type of Pokemon only on the basis of its stat totals. Now, today's discussion is more towards some fundamental questions pertaining with can we build a classifier to identify that kind of legendary Pokemon, which is there. So we had the data, which was very rich in that regards. Is there a possibility that we can relate some important variables, or there is a possibility we can narrow down on certain important key features or factors which would suggest us which is the strongest Pokemon character, weakest, which is the most legendary. And the idea was to find out factors which contribute the best in terms of getting the topmost or the strongest Pokemon out in the market so that we can build upon multiple characters based on that. So that was the overall objective. But mind you, today our focus is majorly upon how we did the feature selection process, how we did the dimensionality reduction, how we moved from simply exploring the data to reach to a level where we were able to reduce the dimensionality problem to a manageable extent and come up to a level to say, can we linearly classify the data into certain classes? to help us understand that each class can result in prediction of the Pokemon character. So the overall objective was pretty much in that direction. Now, as I'm going to go ahead, I'm going to take you on to the data as well. But before we jump onto that, I just want you to get familiar with certain important data components which were there in our data set. So simple names like English name of the Pokemon, the Japanese name to it, the Pokedex number, which was kind of an, you can say the index which was given based on the number they were entering into, percentage of male as a percent of the total, because there were genderless Pokemon as well. So there is a primary and the secondary type of the Pokemon. There was a classification described because of Sun and the Moon Pokedox, height and weight of the Pokemon, the capture rate, the base X steps. So the count of the steps that are required to hatch an egg for the Pokemon is the base X steps, the ability that the Pokemon is capable of having. So these are kind of strings. So they're explained in terms of their ability. So experience growth, their happiness base number. So there are 18 variables which we're talking about their against number. So I'll take you on to the data and talk about that, which will show about the amount of damage taken against a particular attack by a particular type of a Pokemon. So the base horsepower, the attack, the defense, the special attack of the Pokemon, the special defense, the speed, the generation, and whether the Pokemon is a legendary or not. So it's a simple classification. Now, important thing to note here is these variables were of utmost importance for us to understand because we are starting dealing with EDA and then LDA, which is about first we did the exploratory analysis, kind of understood what's happening in the data, what's the detail that we can extract from that, and what more can we learn about the characters and the features, and then moving on to doing the dimensionality reduction. So that's broader context under which we wanted to set up this problem. And the interesting piece was that we were not sure of how to begin with this problem because it was unique in its own way. We never knew what we should take as a target variable. We were not sure whether we should take the legendary type as our target variable to make it a classification problem. We were not sure whether we should take any base number, like a base happiness, or the attack or the defense special strategies as some important character. So the idea, what I'm trying to say is, sometimes when we are presented with a problem, we don't know what to achieve out of that problem. The problem is known to us, but from a data perspective, we don't know how to put that into a perspective that we can define technically that problem. So moving forward, these were the kind of hiccups that we had, the challenges that we were facing. So we went ahead and we were sure that one thing that we have to do is do the EDA, do the preliminary analysis on features, and try and see whether we can compress on certain important features. So the same way we kind of started that. So on the code side of it, I'll discuss that step of EDA before LDA. But right now, since our focus is on the LDA piece, I'll discuss a little bit about LDA before going ahead into the code. So the question that comes in is, what is this LDA? What is this feature selection approach? What is this dimensionality reduction kind of a setup? Now, LDA is called as a dimensionality reduction technique. The simple way that you can imagine dimensionality reduction is that whenever we have large number of features, when we say large number of features, it is a count which is not manageable simply by looking at the features. You can't just club them, or you can't just say whether they are kind of related to each other or not related to each other, or that together have an impact on a predictor variable or a target variable. Sometimes we don't know that. So the best way to kind of understand that is try to create certain kind of dimensionality reduction based selections which would help us reduce the n-dimensional, let's say, space into a manageable k-dimensional state. What in simple words that means is we are trying to control the number of features without losing the important or key information, the key variables in predicting or in classifying our target variable. So the objective is, before we jump on to do any kind of pattern classification or any type of machine learning application, the pre-processing stages select the right features. To do that, we apply what is called as dimensionality reduction. Now, as I mentioned, it's a stage before the final application of machine learning. We use it for feature extraction. The idea is, if you look at the small graph on your right, this is one of the finest graphs that is used to denote what we call as the classification of my data into certain specific type of dimensionality reduction. So you see, just by drawing my two important lines here, you see this and this, I'm simply able to classify these three pieces. And these are nothing but linear cuts. What do you mean by linear cut is, I am able to discriminate between this cluster and this cluster on the basis of a linear classifier. Similarly, this cluster with this cluster can be classified simply by a linear classifier. Technically, it kind of becomes very, let's say, imaginative. But when we do it mathematically, it is nothing but a separation of the average value. So let's say, if you look at this graph, right, and pick up an average value somewhere in the middle, we start to measure the distance of each of these yellow points from that average and try to measure that distance. Similarly, for these particular, let's say, feature value, so this all is one feature. You can say this is the speed of the Pokemon. You can say this is the base happiness of the Pokemon. You can say this is nothing but the growth or the capture rate of the Pokemon. So what we are trying to say is the average of the capture rate, when it is compared with the most values of the capture rate, the average of the speed with respect to all the speed values, their distance is kind of structured in such a way that if I draw a straight line, if I go on ahead of that straight line for the speed, it would not have those speed characteristics in it. So that means I would move away from speed and enter into the pace happiness or any other growth variable or very capture rate, whatever variable I was taking it here. So the question under consideration is, can I define that space? And then I can classify that on a linear basis. This is the graphical understanding of what we call as LDA. Hope that makes sense. I mean, of course, I'd be happy to take up questions, but you can keep pushing those questions in the chat box that I can take up towards the end. So it's technically a simple reduction of a data set when we are talking in terms of, so what I have actually done here is from 3 dimensions, just have an understanding. From 3 dimensions, I'm only going to talk about these 2 lines, which means if something lies on to the lesser value of this or something lies to the lesser value of this line, I can say I can classify these 3 features simply on the basis of the distance between their averages. So I've been able to reduce my dimensionality of 3 to 2 by dividing it using a linear transformation or dividing it using a linear discriminant process. That's the idea. So what we do here is we talk in terms of linear separability, and in the data we are able to draw that linear transformation and divide my data set. That's the overall concept of LDA. Now the question that comes in is, how do we do it? So in this problem, technically, we are trying to reduce an n-dimensional problem or a d-dimensional to a k-dimensional where k has to be less than d. So what we must know is that whether our featured data set, which is all the variables, are well represented. Now, if the variables are all well represented, we can compute what is called as eigenvectors. So since I'm not sure if I can see the chats right now, but my obvious question to most of the people at this point would be, please understand what is an eigenvector. So people who come from a little mathematical background would be able to tell you that eigenvectors are nothing but for a matrix. Matrix means the data frame that we create in case of our, let's say in a Python or in R or in a machine learning setup, we convert our input data set into a kind of a data frame within which we perform our various transformations or various processing of the data that is supposed to happen. So eigenvectors are a special set of vectors which has linear system of equations, which means these are known as, sometimes we call them characteristics vectors, or we also call them latent vectors. The idea is we are describing the key characteristics of the data using matrix. The matrix has certain set of equations which are being represented as linear set of equations, and we try to solve them. And for these set of equations, we have what we call as eigenvalues. So eigenvectors are connected with nothing but eigenvalues, which primarily denote the kind of loading that we're going to go ahead and talk about, and the coefficient values in terms of our features. Now, it might sound overwhelming in terms of the concept, but when we do it with the data, you will try and understand it much more easily. So once we have the eigenvectors from the data set, we put them in a scatter matrix just to see how the plot looks like. Do they kind of overlap? Can we kind of classify them? Can we put them into a different kind of a structure? So something that I showed here. So just this is nothing but a scatter plot. So if a scatter plot can be used to generate a k-dimensional data from a d-dimensional data set, is the target of what we call as LDA. So idea is, as I simply said, move from a higher dimension to a lower dimension for managing the data better. Now, what happens within the whole process? What you see in front of you is, you can assume this to be simple, a distance between the scatter matrix, which is, let's say, this is my one class, this is another class, and this is third class. So there is something called as scatter matrix within the class scatter matrix, and something which is in between the class scatter matrix. So something that we calculate as a distance between the two classes, and something that we calculate within the class. If you would have done something like analysis of variance, if you're aware of simple terms like standard deviation, covariance, what do we do in all that is we try to assess the distance of my data variable value from its average. Same thing we do it here. The only difference being, now we calculate two distances. So we call SW as the sum of all my, let's say, distances which lie from the average to that data value. So we kind of add those all feature values for specific number of values for that feature. So in our case, we were dealing with 802. We kind of reduced it on the basis of the type of Pokemon. We'll talk about that. And then we consider what is called as the in-between class scatter matrix, which is from one class to the other class, how much is the deviation or how much is the distance. And the idea is we try to create an optimization problem wherein the distance within the class is minimized and between the class is maximized. I think you will understand. The idea of this is I should have a classifier, this line, which is designed in such a way that distance between the blue points with respect to its average is the minimal, and the distance from the average of here to the distance of the average from here should be maximum. Only then this line would be able to classify these two. Hope that makes sense. So the overall objective of LDA is primarily to do this: maximize the between class measure and minimize the within class measure. So overall objective is maximize SB minus SW or minimize SW minus SB. You can frame the optimization problem pretty much the way you want it. It's a simple OR issue. But the question is, you must understand what we are trying to achieve out of here. Idea is within the class, whatever measure we are picking, whether it's a distance, which is based on simple Euclidean distance, Mahalanobis distance, or any distance that you want to define, it should be minimal between the class measures and maximum when we are talking in terms of in-between class measures. That's the quick distinction that we have to understand between the what we do in the LDA. As a process, in simple layman terms, what are we doing at the back end? So what do? We start with creating a d-dimensional mean vector, which in simple words means whichever variables we want to use, we kind of create a matrix, and that matrix is used to denote a d-dimensional mean vector. Now, using that vector, we compute a scatter matrix, which is nothing but the correlation matrix between all the variables under consideration. Once we have those scatter matrix, we calculate the eigenvectors, which I mentioned as nothing but set of linear equations satisfying certain conditions. Once we have the eigenvectors with us, we kind of calculate their eigenvalues, which is nothing but, if this is a matrix, this is a determinant. There are relationships which are predefined for getting eigenvalues from the eigenvectors. We sort them. Once we sort them, we get the largest eigenvalues to form a D cross K dimensional matrix. So don't get overboard with the mathematics behind it, because once we do it on the data, you will understand it much better. Now, once we have this sorting done, we then transform the sample onto a new space by considering the most highly loaded vectors in terms of their coefficient values. So the coefficient attributes comes out as a final value for us to feel which of the features are important. Then there are feature loads. These are related to the phases. You would see what is coming out as an output from each stage. And this is the final objective of the LDA. We want to find out what are the coefficients of the attributes that we are using. Because once we have these coefficients, we would be able to make use of our understanding from the business that whether or not these coefficients contribute towards the creating the linear classifier, which can help us reduce our overall dimensionality. So that's, in a broad sense, what we try and achieve out of LDA. Now, for our problem, this is the snapshot. So we had the data with us, which I'm going to show you right away. We did the basic exploratory, we prepared the data, we kind of moved the null values, we found the relationship, we applied the 5 fundamental steps of LDA, and the overall picture looked like this. So we got the 2-component decomposition looking like this, which in the next 20-25 minutes I'll explain you what this means. We got the scatter plot, the feature coefficient plot, where we got the vector loading happening. From here, we were able to find out which of the features are loaded with the highest coefficient values, so that we can understand which of the characteristics are weak, which of the characteristics are strong, in identifying with the special characteristics or in the special features of Pokemon. So that's in a nutshell, and that's in a broader way to look at what we kind of did. Try and look at the columns that we have kind of spoken about, the titles, and these are all the ones that I showed you on the first slide of the deck. So the first column, as I mentioned, is the strings, where we are defining the abilities of my Pokemon. So you can see overgrown with the chlorophyll, blaze, solar power, shield dust, runaway. These are certain characteristics which are defining the Pokemon in terms of its abilities, of what it is capable of doing. Now, these are the 18 variables that against we kind of mentioned. So if you look at on the Jupyter Notebook, we started with importing the important libraries, which I'm sure by now you guys are familiar that to perform the basic data framing, basic statistical or mathematical, let's say, calculations, plotting using multiple libraries, some important description statistics that we want to do, we may use these specific libraries. And I think in your technical classes on Python, you would have kind of spent a good amount of time in understanding these, what are these, what is the background and all. So read the data, and you can see here we are plotting. Maybe we can have a look at the data here also. If you see, these are those 18 variables that we were talking about against bug, against dark, against the dragon, against the electric. So these are 18 variables which are kind of defining the ability of the Pokemon to react to. So against different scenarios, yeah. Now, this is the percentage of male, the Pokédex index, the special attack, special defense, the speed. There are two different types of Pokemon that we have kind of used. So we have the data here. It's the same problem, yeah. So speed, type 1, type 2, the weight. Some of the variables are missing here. I'll just show them in the Excel. The weight, the type of generation out of the 7 generations we were talking about, and a classification variable to talk about whether it's a legendary or a non-legendary Pokemon. Some other variables which are there, you can see against ice, noise, the normal, the poison, the psychic, the rock, steel. So we have all the variables being here. Apart from that, there are the hatching steps that we mentioned, how many steps it takes the Pokemon to hatch an egg. These are given. Base happiness is being measured on a specific parameter between 0 to about 140, if I remember it correctly. That's how they're measuring. There's a total to the base. There's a capture rate. There's a classification of the Pokemon character. There is a defense score, some experience growth, height, HP, Japanese name. So what I'm trying to say is, the more time you spend on the data, the more clarity you get as to what to do with it and what exactly we can extract as part of the information from that data set. Now, we wanted to understand, can we do more from this data? Now, very openly, very honestly, if I would have been asking this question to you all, these are not something, the ideas that come out very naturally. This is something that we kind of experiment with all the time. Now, as you see in front of you, you can make out that we defined meaningful variables like the base stats and the mod stats. These are not something which are common to come up with. So when we don't understand that we are unable to classify a particular data, or we are unable to, let's say, analyze the data better, we kind of start to club the variables. We start to create our own variable. We start to attack the problem from a different perspective. So you see what we did, we defined most of the meaningful variables as base stats and mod stats. So in simple words, we were trying to find out, can we define the strength of a Pokemon? Yeah, based on its offense versus defense strategies, because we understand that the overall objective is to attack and attack first. So that's the competition all about. Now, you can always play around with multiple strategies. Of course, in a game, you can come up with some defensive strategies sometimes and very, very attacking strategies. That's very fair. But we had to go by an assumption, right? So what we did, we created these stats, we created these basic features, and saw that how the data changes and how the graphs could actually give us more understanding of what's happening with the different generations of the Pokemon. What is happening with the different legendaries of the Pokemon. So idea is, moving from 1 generation to the 7th generation, how these base stats started to differ. And when we say base stats, you can see these are our base stats. So we picked up as attack, defense, the HP, the special attack or the specific strategy for the attack and defense, and the speed, we considered that as our base statistics, because these are characteristics of the Pokemon which describe their basic strength. Let's put it this way. So we started creating our own variables. So what we did, we created some mod of attack, which was nothing but, let's say 150% of the initial attack variable value. Similarly, for speed, we doubled it. Similarly, for SP attack, we 1.5 times it. There is a complete different discussion of why we did what we did. I mean, we can always discuss offline, but I hope you're getting the idea. The idea is, we were trying to create newer base stats and the mod stats for us. We wanted to identify, are we able to gain better insights into our data by doing this? If yes, what is it that we can try to work on? So we kind of did that. Let me just bring this down for clarity. So you see, the base stats for Pokemon, we defined it as a simple sum of all the key features. So we kind of picked them up and we were calculating the base stats. We got the off stats, which is the offensive strategy. Now, for offensive, we have to consider more of an attacking characteristic. So you see Pokemon attack, the special attack, and the speed. These were considered for the offensive strategy. In case of defense, we were considering the Pokemon defense, its HP, and the specific defense strategy or the defense speed. So what we are trying to say is we were creating newer variables to have an insight into what's happening, or to have an insight into can we describe the character by putting in more details and by being very specific about certain features and making use and by creating newer variables as well. And then you see the mod stats was we made use of mod attack, the defense strategy, the Pokemon HP, the mod stack attack. So you see all the offensive were covered here, and the defense we kind of added. So to get what we call as a mod stat, we were trying to make it you can understand this was more like a moderate kind of a scenario that we want to come up, something like an average scenario, so that we can compare it against all the other variables. So here the idea is we are overemphasizing on the attack strategy so that we can kind of compensate for the defense pieces as well. I hope that makes sense, but I can answer that question later on as well in case if you have any. What we did rest was to find out what's happening within each of these generations in a way that for each of the generation, we kind of picked up those specific values. And we then had those base generation averages as well. So if you see the base stats we calculated based on each generation, base stats is the base stats that you see here. This was our base stats that we calculated. And these numbers were primarily to denote the generations. And we also classified on the basis of the legendaries, which was, as I mentioned, the 2 legendaries that we could work out. So it was completely based on our understanding of how we wanted to explore the data further. Now we also did what is called as the average of these 7 generations base stats, and you can see this was a kind of an understanding that we got for specifically their abilities against bug and against the dark. I mean, we can print about any of these values that completely depended on us, but all these values you can see that we started to find out classified commonly based on the generations. So for each of the generation, we were able to extract this. You can see for 7 generations, we kind of had the averages value for all the variables. So the idea was, are the generations quite significantly different from each other in their characteristics? We wanted to see that. That was the idea. Now, how could we do the further analysis on the base stat value that we kind of calculated? So it was simple. We can start to plot it. So let's say how we can plot it and what we can get. We can start with all the starter Pokemon, which is generation 1 and the initial starter Pokemon, to start to compare them with their evolved form. Although it was difficult, we kind of labeled it in a way that we can do this completely, because there was a lot of stuff which was available online about the Pokemon. So we started looking at all the 21 starter Pokemon with their base stat value, off stats value, and the offensive and the defensive stats values, so that we can compare with their mod stats with the highest and the lowest, and kind of compare between the various generations. And what we got very interestingly was, if you kind of focus in here, so except for generation 5, where they had all the same base stats value, and generation 3, where a specific Pokemon was able to win because of its extremely high defensive stats, we kind of got the mod stats for all, which is the Pokemon with the highest of stats also had the highest base stats. We kind of found that. So we were able to find this relationship as well. So their offensive strategy and the highest base stat values were helping us to kind of categorize them at the top. So overall, we see that the Greninja, which is the blue bar in the generation 6, is the overall winner in the base stats, off stats, and the mod stats. Venusaur wins with the highest defensive stats. Now, this is all which is coming out of, let me show you what we did as the analysis here. And it kind of started to give us the various starter Pokemon and their base stats value. So these are different bars. Let me show you what these bars basically mean. So if you start to look at closely, what we kind of then did, let me show you where we described the data frame for this. So you focus on here where we have the data frame created for the specific Pokemon that we are talking about. So these are specific ones that we kind of listed. You can see these are the ones that we are kind of talking about. And that's the data frame that we are now using. So for defining the bar graph, we kind of use the number, the name, the base stat values. The Pokédocs number was readily available to us. The generation trick was there, which is just to showcase the position they are in, the various generations they are part of, so that we can know where they are currently. And if you, let me just minimize this a bit so that we can look at the code against each of those values. Now, the idea is we wanted to understand all the starter Pokemon from generation 1 till 7, what are their base stats values? So when we say the base stats value, we are trying to plot the base stats with the generation number and with their values being plotted against. So you see in the first generation, I'm just trying to give you the colors, the green and the red. Yeah, so the generation ticks and the generations are primarily being given in these Pokemon starter values. Question is, what do we understand from here? What is it that we are extracting? What is the analysis that I can perform moving further from these specific graphs? Question was made very clear to us that we can see the trend in the starter Pokemon and their stats values as we are moving away from first to the 7th generation. So even towards the 6th generation, I see the topmost, the blue graph, the blue bar, which is here. Otherwise, the graph has come down completely. What is it telling me? The base stats values have been going down. That's from generation 1 till generation 7. We can see that in the first and the third generations, these values were still all right. But apart from that, all the Pokemon values of my base stats were coming down. What does that mean? Let's look at some other offense stats as well. Look at their offense stats from generation 1 till 7. So the base stats is a more, let's say, normalized kind of a number. Whereas the offensive stats show us the different variation that is coming across. And if we look at their defense stats, you would know that they are pretty much always have been working with them. Now let me put all these things into perspective. Please understand this. Generation 1, 2, 4, and 6 have the best starters and their best defensive stats. Let me just put this. You see this here. 1, 2, 4, and 6. Look at this. 1, 2, 4, and 6. What we say by this is their starters and their defensive stats are the best, which is compared with any of the others as we look at their defensive stats. While when we compare if we look at offensive stats, the first hit and killing with that hit, we find that it is the first, third, and the fourth, which is red is more like an attacking one. So we can find this is in first, third, and a little bit in fourth, being the being the highest in terms of the offensive stats that we can compare. Idea is generation by generation, the Pokemon starter is showing different types of strategies, which is more attacking, more defensive in which generation. So different generations had different base stats scores, which leads to different their defense stats and difference in their offense stats, which kind of was telling us that we would need these variables to understand their overall stats as well. So what we did, we kind of did the modulars, which is more like a moderate stats, where we were trying to put everything together so we can average that out. We kind of plotted those to see for those specific key, let's say, generation number. We wanted to find out for all the starter Pokemon what's happening as far as their moderate stats is concerned. So you can see that if you look at the moderate stats are also varying pretty much, and they're coming out very similar to as we were looking at the base stats. So the average of all this starter Pokemon was trying to give us that they had a balance across the 7 generations when they were considering both their offensive and defensive strategy. That was something that was happening. So I'm taking a little bit zoom out from here because the EDA part of it can be expanded into any extent, because here we were trying to find out strength. We tried printed this. So you can see that highest base stat starter Pokemon was Greninja. The lowest was the Meganium. The highest HP starter was this. Highest attacker starter was Blaziken. Special attack. So this was very simple for us to find out based on their special attack, special defense count and the speeds that we kind of calculated. So we were able to find the highest and the lowest across different type of the Pokemon that we were looking at within the starter Pokemon. And we could also see their distribution. So we wanted to see their distribution with respect to their HP. We wanted to see their distribution with respect to their attack. So we wanted to see their distribution with respect to, let's say, SP attack. So you could see this is very, very comparable and normalized in a way that across they were showing characteristics which were quite balanced, apart from certain, let's say, variations which were predominantly not expected. But yeah, so what the idea is, why I'm rushing through this is simply because of time, is that you can study this EDA, so you get the idea that we can do so much more onto the variables by creating newer variables. So that was the objective of showcasing you that, and we did a lot more with the starter weakness analysis as well. But let's just take a step back and try to come back to the objective of the session, which is I wanted to see whether LDA can be performed and I can reduce my dimension using a linear discriminant analysis. So what we did, so we thought that we're going to avoid the overall mangling of the two different types of Pokemon, type 1 and type 2. So we only picked up type 1, wherein the type 2 was kind of missing. So wherever there was 2 types given, we were trying to avoid that. We were only looking at wherever the type 2 is null. So you see the DFV that we kind of created, we kind of took that as our input and did the normalization. Well, let me tell you, the normalization is not like a mandate, but it's just to size the numbers in a specific, let's say, level. That was the objective. Now, this is where the basic LDA kind of component comes in. So all the math and all the difficult pieces that we kind of discussed in the deck can be simply summarized by applying the sklearn discriminant analysis, which is the package which is readily available. You can easily pick it up and go on to apply that. But we kind of applied the LDA components to it, and we got the linear discriminant playing its role. Now, let me put you into a different kind of situations. So I'm not getting into the code part of it, because that's a very simple code to plot the feature coefficients. But this is the heat map. Yeah. So let me reduce the LDA feature coefficients. And I want you to spend a minute to just look at which of the features that you see at the bottom, which is SP attack, SP defense, attack defense speed, HP. These are my vectors. And these are the various characteristics against which, so these are those 18 characteristics against which the Pokemon have been led out. So the idea is, which one do you see is loading well on these vectors? Means, which of this is contributing to these vectors? Just spend some time analyzing values which are quite big in terms of positive or quite low in terms of negative, because both are kind of helpful to us. So if you look at, let's say, this rock that you see very much in red, it loads very well, which means it's at a pretty high loading value. If I look at, let's say, host, you see pretty high loading value. Fighting is a high loading value. Fairy and fighting has a pretty high loading value. I have pretty high loading value at bar. On the other side, let me show you something which is, you see the water at the bottom, very low values. You see ice with very low values. Normal is also all right, but it still has one value which is heavy. What I'm trying to say here is, with a very simple LDA feature coefficients comparison, we could see some of the variables or some of the features getting heavily loaded and some features not. So in this heat map, this is what we are able to see. So rock type, which is, if you look at this rock type, so it loads very strongly on all of the special attacks, special defense. And so what we can say is, the rock archetype of Pokemon is clearly coming out by studying its SP attack, SP defense, attack defense, speed, HP characteristics, because we are able to see the lot of dependency of this archetype on these characteristics. Whereas something like ice and water, they have very little separability, which in other words means that I won't be able to classify or separate them on a linear basis. That's the objective. That's the overall idea of whether we can apply LDA or not. Now, the same thing can be done by calculating their coefficient sums. Very simple. I mean, what I did a kind of, where we found these coefficients, now we are adding them to see how they sum up. So this is more in terms of magnitude. And you can see rock, host, poison, fighting. These are pretty much a predominant variable, which can be very well useful in defining their key characteristics, so to say, as such, which can tell us that these are my easily definable characteristics to identify my most predominant features for a particular type of Pokemon, of course. Now, finally, we wanted to find out whether there is a possibility to divide it into a linear classifier or not. For that, what we had to simply do is put the categories onto a map, which can give us a scatter plot to show the LDA decomposition, which what it means is something like this. So you see all my different components that I was referring to. How are they distributed across the two components? You can say C1 and C2. These are my two different types that I'm trying to basically highlight and compare between the LDA decomposition type. Now, my question open to all, and we will take another part of discussion is this scatter plot that you see in front of us, can I distinguish the features, which by features I mean, can I distinguish predominantly the different characteristics that you see in the graph using some linear space? Now, that's the overall objective of an LDA. If that is a possibility, we can distinguish that. If not, we will never be able to classify our data or reduce the dimensionality using LDA, which means the problem will then can't be handled by a linear composition. We will have to deal with a non-linear classification, which means the dimensionality reduction cannot happen using a linear discriminant analysis. And we will then have to go to a non-linear discriminant analysis, which means if you start to see the categories that we have taken here, by categories I mean we are defining a certain, let's say, key variables. Let me show you. This was my explained variance ratio with the component that we were dealing with, and the idea is that we take the top 3 explained variances of the decomposition. Now, PCA tries to maximize these values. LDA maximizes the difference between the classes. In simple words, as I mentioned, that we look at the average value and try to see how much they vary with all the different values within that class. And of course, across the other class, and it tries to maximize the distance between different classes and minimize it within the class. The idea is, if I look at those 2 classes, C1 and C2, my classes are not getting distinguished. Which means what? A simple conclusion, that I cannot linearly classify the current set of features into a linear space, which gave me a very good understanding that to predict on the basis of these features would be very, very difficult. We did that again by using SVM, because SVM gives a very different cut to the data. We were able to do that. But as a conclusion to this particular study from LDA, we were able to conclude that a linear classification to this particular data set is not practically possible, although there are certain important characteristics which are heavily loaded. But still we cannot classify based on a very simple linear transformation. We will have to do a non-linear transformation.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.